All right, so number one, we're finding the pH. Again, pH is equal to the negative log of the H3O concentration, which is the same as the H plus concentration. All the same thing. So, in letter A, they're giving us the H plus concentration. So all we have to do is plug that into this equation. Negative log of 1 times 10 to the negative 4th. And that's going to come out to 4. Anytime there's just a 1 in front of the times 10 part, whatever the exponent is, that's what the number is going to come up to. For letter B, they're giving us the OH concentration, which we could use to get the POH, but we can't use it to get the pH. So again, there's a couple ways we can go about this. I'll do letter B one way and then letter C the other way, just for fun. So again, the H3O concentration times the OH concentration always equals 1 times 10 to the negative 14th. So since they gave us the OH concentration, we can take 1 times 10 to the negative 14th divided by the OH concentration. And that'll give us the H3O concentration. And this should come out to 1 times 10 to the negative 12. Then we can take that and stick it into the equation for pH. And we got a pH of 12. So that's one way we can do it. Questions about that? The other way, my preferred way, to be honest, is if we know the OH concentration, from that we can get the POH. POH would be the negative log of the OH concentration. So 3.5 times 10 to the negative 5th. And that comes out to, again, make sure you're using the EE button. So this comes out to 4.46. Well, let's keep everything to the tenths place. I'll call it 4.5. But again, that's POH. And from that, we know that pH plus POH would equal 14. So pH would equal 14 minus the pOH. So we take 14 minus the 4.5, and we got a pH of 9.5. Questions about that one? So again, there's a couple ways you can go about it if you want the pH, but you have an OH concentration. Letter D, we've got the H3O concentration. So we can just plug that right into the equation. pH would be the negative log of the 7.1 to the negative second. Which is 1.1. All right, number 2, we're going the other direction. We've got the pH or the pOH, and we're looking for the H3O concentration. So, again, taking the pH equation and rearranging it for the concentration means that the concentration is equal to the antilog, which is the second function of your log key, of the negative pH. Instead of the negative log of the concentration, it's the antilog of the negative pH. So, this first one is antilog of -6. And if we got a whole number, that's going to become the, you're going to have a 1 in front of the times 10 part, and that whole number is going to become the exponent. So that one's 1 times 10 to the -6th. Means this one's going to be 1 times 10 to the -3rd. And then again, with if you're looking for the hydronium ion concentration and you've got a pOH, there's a couple ways to go about it. So once again, I'll show you both ways. From pOH, we could find the OH concentration. Which would be the antilog of the negative pOH. So the antilog of -12 would be 1 times 10 to the -12. That gets us our hydroxide ion concentration. From there, to get the hydrogen or hydronium ion concentration, we go back to this thing. Since hydronium and hydroxide concentrations always multiply to 1 to the negative 14th, we can take 1 times 10 to the negative 14th and divide it by the OH concentration. The other way, and again my preferred method, is since we have the POH, get the pH first by subtracting this from 14. So our pH is going to be 10.35. And then you can find the hydronium ion concentration from the pH. It's going to be the anti-log of negative 10.35. Make sure you stick that negative sign in there. 4.47 to the negative 11th. Questions on those? Number 3, calculate pH. So in this, they give you a concentration with a formula. You have to realize which one you have. So in letter A, we have 2.5 times 10 to the negative third molar sodium hydroxide. That ends with OH, so this is going to be your OH concentration. There's only one OH in the formula, so this is equal to the OH concentration. So from that we can get POH. So our POH is the negative log of the 2.5 to the negative third. Which is about 2.6. And then for our pH, we can subtract that from 14. We have a pH of 11.4. For letter B, we have a formula that starts with H. So this is going to be our acid. We can get our H3O concentration from this number. But since there's two H's in the formula, the H3O concentration is going to be double of this. It should just be 5 to the negative third. We'll double check. Yes, 5 to the negative third. Okay, so again, we have to double this concentration because there are 2 H's in the formula. Now that we have our H3O concentration, we can plug that into the formula, the equation. And negative log of 5 to the negative third is about 2.3. Letter C is the same situation. It's actually the same acid. So we have to take the 7.5 to the negative second and double it. Which is 1.5 to the negative first. Honestly, it's a lot easier to just enter as 0.15. So then our pH is negative log of 0.15. Which is 0.8. Questions so far? All right. Letter D, we again have an acid. This time there's only 1 H in the formula. So this is our H3O concentration. Negative log of 4.8 to the negative second is 1.3. Letter E, our formula ends in OH, and only 1 OH, so this is our OH concentration. So from that we can get POH. Which is 1.5. And then to get pH, because that's what they're asking us to find, we subtract that from 14. And then for letter F, we have a formula that ends in OH, but it has 2 OHs in it. So our OH concentration is going to be double of this number. is 3.4 times 10 to the negative 4. So then we can get our POH from that. Which is about 3.5. And then subtract that from 14 to get our pH. Questions there? Anybody not done looking at this? Right. Number 4, same type of thing, find the pH, but also indicate whether it's acid or base. pH below 7 is acid, pH above 7 is base. So in letter A, we again have a formula that ends in OH. So from this number, we'll be able to get our OH concentration. It's going to be 2 times this number because there's 2 OHs in the formula. So that's going to make it 1.402 to the negative 5th. For the OH concentration. From that, we can get POH. Which is about 4.9. And then subtract that from 14 to get our pH. And that's above 7, so it's base. Letter B, we've got a formula that starts with H. There's only one H in the formula, so this is our H3O concentration. We get pH directly from that. Negative log of 9.47 to the negative 6th is about 5. That's below 7, so it's acidic. And for letter C, starts with H, but there's 2 H's in the formula. So we have to double this number to get our H3O concentration. And that is 0.01318. And the negative log of that is about 1.9. Which would make it acidic. Questions on those? Okay. Moving along to these. So letter A, if the pH is 3.56, what's the OH concentration? To get OH concentration, we want to take the antilog of the negative POH. Since we have the pH, we can subtract that from 14 to get the POH. It's 10.44. So we got antilog of negative 10.44. Which is 3.63 to the negative 11. Letter B is basically the same thing, we just flipped it around. Give the OH and ask for the H concentration. H concentration, or H3O concentration, would be the antilog of the negative pH. If our POH is 12.45, our pH is going to be 14 minus 12.45, which is 1.55. So antilog of negative 1.55. Is 0.028. Questions so far? All right, letter C, they gave us the pH, they want the H concentration, which again is the H3O concentration. So this time we don't have to do anything ahead of time, we just put it straight into the equation. Antilog of the negative pH, which is 5.15. And that comes up to 7.08 times 10 to the negative 6. And same thing for letter D, pretty straightforward. Well, I guess it's not. They gave us the OH concentration, but they want the pH. Again, I prefer getting the POH concentration. So if I take negative log of 2.37 to the negative third, it's about 2.6. And then to get the pH, you subtract that from 14. We got a pH of 11.4. Questions on any of those? Okay. For number 6, we're just labeling these as Bronsted-Lowry acid or base. It didn't specify, but that also means you're supposed to label the things on the right side of the arrow as the conjugate acid and conjugate base. So, again, under the Bronsted-Lowry theory, an acid is something that donates a proton, or in other words, a hydrogen. So as we go from left to right, it's going to lose a hydrogen. A base is something that accepts a hydrogen. So as we go from left to right, it's going to gain a hydrogen. So if this starts out as NH3, ends up as NH4, it has gained a hydrogen or accepted one. So that makes it the base. H3O ends up as H2O. I'm not sure why there's an extra plus sign in there. So that loses a hydrogen. So that's our acid. Whatever started out as the base is going to become the conjugate acid on the other side. And the thing that started out as our acid becomes our conjugate base. And again, another way of looking at it is if you go in reverse, this stuff gives up a hydrogen and this one accepts it. I guess for those of you that might actually be watching this video, this stuff accepts the hydrogen if we go backwards. Just kidding. This stuff gives up the hydrogen if we go backwards, and this one accepts it. Okay, we'll do these other ones a little more quickly. We're recording. Alright, so let's see. This one loses an H to become CH3O. So that's our acid. This one goes from NH2 to NH3, so that's our base. That makes this our conjugate base, and this is our conjugate acid. In letter C, the OH picks up a hydrogen to become water, so that makes this our base. The H3O gives up a hydrogen to become water, which makes this our conjugate acid. Since both of the things on the right side are water, it doesn't really matter which one you label which, but just keep it in order. If the first one was our base, it's going to become our conjugate acid. I don't know why I put C's in front of these over here. That would be base, that would be acid. So the conjugate acid and this one conjugate base.
Well, I know we're doing a review. I was like, what are we doing?
This is actually the pH assignment. So, again, in this one, we're identifying these as Bronsted-Lowry acids, bases, and conjugate acid, conjugate base.
I'm cooked. I do not.
So, once again, an acid gives up a hydrogen, a base accepts it. H2O becomes OH, so that gives up a hydrogen, so that's our acid. NH, this should be a 2 down here. NH2 becomes NH3, so that picks up a hydrogen, so that's our base. What was our base becomes our conjugate acid on the other side, and what was our acid becomes our conjugate base. Let's finish it off with the green.
Oh, I don't like this game.
Bro, I'm recording. Don't roll in here 40 minutes late with all this wild stuff. Alright. H2O picks up a hydrogen to become H3O, so that's our base. HClO4 gives up a hydrogen to become ClO4 negative, so that's our acid. What was our base becomes our conjugate acid. What was the acid becomes the conjugate base. Easy like a Sunday morning. Questions about that?
Oh. What do I look for when it comes to the PCAs, CVs? Like, okay, I know.
Again, the hydrogen, under this theory, the acid is going to lose a hydrogen. So you're looking for the thing that has a hydrogen on this side and either no hydrogen or one fewer hydrogens on the other side.
So we're looking for the numbers.
Okay.
And the numbers.
You're looking at the number of hydrogens in each formula.
Okay, so this.
Okay. This one goes from H2O to H3O. So that gains a hydrogen, which makes it the base. So an acid gives up a hydrogen, a base accepts one.
So, okay, yeah, I think I'm good. I think. And where does the C come from? I can just put C, but.
That stands for conjugate. That's what they're called on the. That's what they're called on the right side. Conjugate acid, conjugate base.
Okay, so it's always on the right side.
Yes. Left side will be acid base. Right side will be conjugate acid, conjugate base.
Okay. And then then you're just looking for the number of H's, and if it decreases or increases, and that gives you if it's a better fit for